Usually when we think about teamwork, there's this expectation of visible communication.
Right, yeah.
Like, picture a sports team on a field, right? A point guard calls a play, the player's not, everyone moves to their spot. You can literally see the coordination happening in real time.
Totally.
But step into the world of artificial intelligence, and that visible playbook it completely vanishes. So, welcome to the deep dive.
Today we have a stack of state-of-the-art research papers, and we're looking at one, frankly, terrifying and fascinating question, which is, how do you get artificial minds to cooperate when they can't even see each other?
And that question is exactly what makes the preprint paper we're unpacking today so significant. It's titled, Bridging MARL to SARL, an order-independent multi-agent transformer via latent consensus.
Catchy.
Yeah, very technical title. But behind that, it's really the secret to how AI agents are finally learning to work as a unified team, like without stepping all over each other's toes. So whether you're trying to figure out how autonomous ride-hailing fleets will coordinate in the near future, or, you just want an aha moment about how AI makes decisions behind closed doors, this deep dive is for you. We're going to skip the heavy jargon and get straight to the actual mechanics of AI teamwork.
But to really appreciate the fix, you need to understand the baseline problem first. We're operating in a field called cooperative multi-agent reinforcement learning, or MARL.
Okay, MARL. Got it.
Right. And the goal here is not just getting AI to beat video games. We're talking about solving massive real-world logistical nightmares. Think about an entire city's traffic grid during rush hour.
Oh, wow. Yeah.
Where thousands of traffic lights need to adapt dynamically, or, a swarm of hundreds of robotic drones scanning a mountain range for a lost hiker.
Okay, let's unpack this. Because that sounds great in theory, but I know there's a massive roadblock here. The paper refers to it as the curse of dimensionality.
Yes. That is the core villain of the story here. In a single agent system, the AI only looks at its own little world, right? And it chooses from its own list of actions. But the moment you add a second agent...
Things get messy.
Exactly. Then a third, then 100th.
Yeah.
Mathematical space. So the combination of what everyone sees and what everyone can do, it doesn't just add up. It multiplies. It grows exponentially.
So instead of trying to solve a chessboard, the AI is suddenly trying to solve, like, a chessboard the size of a galaxy.
That's a great way to put it, yeah. And traditional training methods just collapse under that weight. The environment becomes highly non-stationary.
Meaning what, exactly?
Meaning every single agent is learning, adapting, and changing their behavior at the exact same time.
Which sounds completely impossible to manage. I mean, if I'm an AI agent, how do I learn a strategy if my teammates keep changing theirs every 5 seconds?
You don't. The system just becomes unstable. So to get around this exponential chaos, earlier researchers tried this logical workaround. They said, if everyone moving at once is too messy, let's just make them take turns.
Okay, sequentially.
Yeah.
Like playing a board game.
Yes, exactly like that. That was the idea behind the multi-agent transformer, or MAT. It uses an autoregressive process, generating actions one by one.
Yeah.
Agent 1 moves. Then Agent 2 looks at what Agent 1 did and makes its move. But this logical step actually created a massive fatal flaw, which is the order-dependent bias.
Order-dependent bias, meaning whoever goes first is at a disadvantage.
Actually, it's much worse than that. It completely breaks the AI's ability to figure out why it failed in the first place.
Wait, really?
Yeah. Let's look at the payoff matrix example from the source material. Imagine a cooperative scenario where the absolute best outcome, the global optimum, requires both Agent 1 and Agent 2 to choose action B.
Okay, both pick B.
Right. And if they both do that, the team gets a massive reward. Let's say 100 points.
Simple enough.
But there's a trap. If Agent 1 acts first and chooses action B, doing exactly the right thing, and then Agent 2 acts sequentially but messes up and chooses action A.
Well, let me guess. They get 0 points.
No, the team doesn't just get 0 points. They are heavily penalized with a negative 100-point reward.
Wait, what? So Agent 1 did exactly what it was supposed to do, but because it had to go first, it gets dragged down by Agent 2's mistake.
Exactly. Because MAT evaluates the timeline sequentially, the system's value estimation looks at the result and says, Agent 1, you chose action B, and it resulted in a catastrophic negative 100 reward. Never do that again.
That is completely unfair to Agent 1. I mean, it's like a terrible group project where you write a perfect essay, your partner forgets to submit it, and you both fail the class.
That's exactly what it is.
So what does Agent 1 do in response? Does it just give up?
Basically, yeah. It completely restricts its action entropy, meaning its willingness to explore new options drops to 0. It gets terrified of that negative 100 penalty, so it converges to what's called a Pareto suboptimal Nash equilibrium.
Whoa, pause. Pareto suboptimal Nash equilibrium. In plain English, does that just mean they settle for a C- strategy because they're too terrified to try for an A?
That is a perfect translation, yeah. They settle for a safe, mediocre strategy. Maybe they both agree to always choose action A for a measly 5 points, just to avoid the possibility of the negative 100 trap.
Oh, I see.
Yeah, they get stuck there, completely unable to ever find that optimal BB combination.
Okay, but look, if the sequence is the like, if Agent 1 always gets punished simply because it goes first, why didn't researchers just teach the AI to mix up the order?
What do you mean?
Like take turns going first, or figure out dynamically who should lead based on the situation?
That's a very intuitive leap, actually, and it's exactly what subsequent models tried to do. The paper explicitly discusses models like PMA, which attempted to dynamically optimize the decision order while also learning the actions.
Okay.
But it failed entirely.
Why? Did the math just not work?
Then the math worked, but the computing power required just exploded. When you ask the AI to optimize the order of agents, you expand the search space to n factorial.
Okay, n factorial. Give me a sense of scale there.
Well, if you have a relatively small team of just 10 agents, 10 factorial means there are over 3.6 million possible orderings.
Over 3 million.
For just 10 agents.
Yes. Now imagine an autonomous driving grid with 500 cars.
Oh my gosh. That's impossible.
Right. It massively increases the training complexity. And even if you could compute it, you haven't solved the core issue. As long as the decision-making is sequential, early agents are always vulnerable to the mistakes of later agents.
So fixing the lineup doesn't work. The line itself is the problem.
Exactly.
Which means you have to throw out the idea of taking turns entirely. But how do you do that without going back to that chaotic, everyone moving at once problem we started with?
That is the central friction this paper solves. The authors of the Consensus Multi-Agent Transformer, they call it CMAT, realized they had to bridge RRL into a hierarchical single-agent reinforcement learning formulation.
Or SARL.
Wait, they turned a multi-agent problem into a single-agent problem.
Effectively, yes. They structured the architecture to treat the entire team of independent agents as one unified entity.
Okay, here's where it gets really interesting, because I was trying to visualize how this works in practice without them taking turns.
Yeah.
It's like, imagine a group of friends trying to coordinate an elaborate surprise party.
Okay.
If they act sequentially, one person buys a cake, the next person accidentally texts the birthday girl. The surprise is ruined.
Right. The early actions get punished by later mistakes.
Exactly. So CMAT is basically those friends using a silent, private group chat to agree on a high-level strategy before anyone takes a physical step.
I like that framing. That's really accurate. In CMAT, the transformer decoder isn't used to spit out specific physical actions for each agent, like move left or accelerate.
Right.
Instead, it generates a high-level consensus vector. It is literally simulating the process of the agents reaching an agreement in a latent mathematical space.
Okay, so they have this mathematical group chat. They agree on a plan.
Yeah.
Then what happens?
Conditioned on that shared consensus vector, all the agents then generate their low-level physical actions simultaneously. No turn-taking.
None at all.
None. It's completely order-independent. Every agent moves at the exact same time, but they do it with full awareness of the high-level strategy everyone just agreed to.
Let me see if I'm getting the implication of this. Yeah. If we go back to that brutal payoff matrix from earlier, where Agent 1 got punished with negative 100 points because Agent 2 messed up, does CMAT actually solve that?
It absolutely does. And the reason comes down to how the system assigns blame.
Okay.
Because the probability of an agent taking a physical action is mathematically conditioned on the consensus vector. If the team hits that negative 100 outcome, the system doesn't yell at Agent 1 for its unconditional choice of action B.
Who does it yell at?
It penalizes the latent strategy itself, the consensus vector.
Oh, wow.
Yeah. The neural network realizes that the specific agreement they reached in the group chat was flawed, not Agent 1's willingness to explore. Agent 1's underlying policy isn't unfairly punished, leaving the system free to keep exploring until the consensus module learns to output the perfect strategy where both agents choose B simultaneously.
That is brilliant. It completely insulates the individual agents from unfair penalties.
Yeah.
But I am still struggling a bit with the how. Like, a silent group chat is a nice metaphor, but how does a neural network actually build this mathematical agreement behind the scenes?
For that, we have to look at the transformer architecture itself. CMAT starts with the transformer encoder, which gathers all the observations from all the agents in the environment.
Okay.
But the authors do something crucial here. They remove the positional embeddings.
Positional embeddings. Wait, normally a transformer reads data sequentially, right?
Mm,
Like reading a sentence left to right, word one, word two. So positional embeddings tell it the order.
precisely. By stripping those out, the encoder is forced to look at the multi-agent observation data without any concept of order.
It's like pouring all the words of a sentence into a bowl and just looking at them all at once.
Yeah.
There's no first agent or last agent anymore.
Right. It becomes a completely unordered set. This collective observation data is then fed into what they call a critic compressor. Think of it as a funnel that squashes all that complex multi-agent information down into a single initial consensus vector. The first draft of the strategy, basically.
And then they iterate on it, right? I remember the paper mentions a transformer decoder takes that initial draft and iterates it a specific number of times using the variable m.
Yes, the autoregressive refinement process. It loops the consensus vector through the decoder, updating and refining the high-level strategy step by step.
Which brings up a logistical question for me.
Mhm.
How many times do they need to iterate? Do they just let the math loop 1,000 times in the latent space until the plan is perfect?
Not at all. That would be computationally disastrous. The authors actually ran a detailed ablation study to find the exact sweet spot.
An ablation study? Is that where they basically turn different parts of the model on and off to see what breaks?
Essentially, yes. They test different configurations to isolate what's actually driving the performance. And the data they found here is incredibly clean. They discovered that iterating exactly in times where n is the total number of agents in the simulation is the optimal choice.
Wow, just n times. So if there are 8 agents, it iterates exactly 8 times.
Exactly. If they iterate 0 times, or even n divided by 2 times, the model fails to generate a strong consensus. The agents simply don't have enough time in the latent space to align.
Makes sense.
But counterintuitively, if they iterate 200 times double, the number of agents' performance actually drops.
Really? You'd think more communication in the group chat would naturally lead to a better plan.
You would think so, but it introduces excessive noise. The neural network essentially starts overthinking the problem and generating redundant information. Iterating exactly in times gives the equivalent of every agent one conceptual turn in the latent space to influence the final strategy.
Okay, so we loop it in times, which means we get in different draft versions of this consensus along the way.
Yeah.
But I noticed the architecture includes something called an actor compressor. What does that do?
Well, a naive design would just take that final nth consensus vector, the absolute final draft, and use it to dictate the physical actions.
Right.
But the researchers found a major flaw with that. Critical information gets lost during the refinement process.
Oh, like forgetting how an argument started once you finally reach an agreement.
Yes, so the actor compressor is designed to mix all the middle-generated consensus vectors together. It takes the first draft, the second iteration, the third, all the way to the end, and squashes that entire set into the final definitive representation.
Oh, that's smart.
Yeah. This preserves the nuances of the negotiation, feeding the full context directly into the simultaneous action generation.
So the final action isn't just based on the conclusion. It's based on the entire thought process that led to it.
Yeah.
I mean, a silent mathematical group chat with perfectly preserved context sounds flawless in theory, but theory doesn't win games.
True.
When you actually drop this engine into a chaotic, real-time environment, does this consensus hold up?
To find out, the researchers threw some of the most punishing benchmarks in the field at this model. We're talking about multi-agent MuJoCo, which is continuous robotic control.
Oh, yeah.
Imagine a robotic ant with 8 separate joints, each controlled by an independent AI agent. They have to perfectly coordinate to make the ant walk forward without it just collapsing into a twitching pile of metal.
That sounds like an absolute nightmare to program.
Yeah.
And they also use StarCraft 2, right? I saw they use scenarios labeled MMM2, 6 versus 8s, and 3S-Fiz versus 6Xs. Anyone who's ever played StarCraft knows those aren't just base-building exercises. They are brutal micromanagement battles.
Very brutal.
They require insane split-second coordination to survive.
Exactly. And for long horizon teamwork, they tested it on Google Research Football, where the AI has to pass, position, and shoot dynamically over a long period.
So across robotic ants, space marines, and virtual soccer, how did CM actually perform?
It consistently outperforms strong, centralized baselines, sequential MARL methods, and conventional models. It beat MAT. It beat the order-optimizing PMAT we discussed earlier. It beat MAT-PO and a model called triple BERT.
But to get those absolute peak numbers, they use a specific training trick, right? The paper mentions an alternating fine-tuning phase.
Yes, and this is crucial for stability. During initial training, the AI is trying to learn how to generate a consensus and how to physically act on that consensus simultaneously.
That sounds complicated for the AI.
It is. This causes mutual interference. It's like trying to learn to read sheet music while simultaneously learning how to physically hold a violin.
The learning curves just clash.
Precisely. So CMAT uses an alternating fine-tuning process. They can do what's called consensus enhancement, where they freeze the physical action policy layers, meaning the agent's physical reactions are temporarily locked in.
Okay.
And the system exclusively trains the math that generates the latent consensus.
Or they flip it. Action policy enhancement. Freeze the group chat, lock in the strategy, and only train how the agents physically execute the plan.
Exactly. And both methods yielded similar massive performance bumps, proving that separating those learning objectives prevents them from stepping on each other.
You know, I want to bring up one specific detail from their ablation study that really stood out to me.
Sure.
We mentioned triple BERT earlier. From what I understand, triple BERT is a baseline model where all agents act simultaneously.
Yeah.
But it does not use any latent consensus vector.
Correct. It's a simultaneous action model without the silent group chat.
Right. So the researchers pointed out something really fascinating. If this whole consensus vector was just mathematical noise, if it wasn't actually helping the agents, the neural network's action layers would naturally just learn to ignore it over time.
Yeah, neural nets are lazy like that.
Exactly. And if CMAT ignored the consensus, it would mechanically degrade into functioning exactly like triple BERT.
But it doesn't. CMAT dramatically and consistently outperforms triple BERT across the board. That is the empirical proof right there. The superior teamwork isn't a fluke of the neural network architecture. It's definitively driven by the agents genuinely relying on that shared mathematical agreement to win.
So what does this all mean? Like, if we zoom out from robotic ants and StarCraft battles, what is the core takeaway for you listening today?
The takeaway is that CMAT fundamentally redefines how we approach fully observable cooperative AI. By treating multiple agents as a single unified entity negotiating in a latent space, we finally have a viable order-independent paradigm.
Yeah.
It proves mathematically that simultaneous action, rooted in a shared high-level strategy, is exponentially more powerful and stable than having agents react to each other sequentially.
And that matters because this is the foundational math that is going to run our physical world.
Without a doubt.
We are talking about the algorithms that will dictate how autonomous ride-sharing fleets actually manage to navigate a busy airport without creating redundant dispatch traffic jams. Or, you know, how a fleet of emergency vehicles can coordinate a green light path through a smart city grid without causing localized bottlenecks.
Right.
They won't be reacting to each other. They will be acting simultaneously based on this shared latent consensus.
Exactly. It moves multi-agent AI from reactive behavior to true synchronized planning. But it also leaves us with a rather profound question as we move toward deploying these models.
Oh, what do you mean?
Well, if AI systems are now achieving this vastly superior coordination by generating highly complex latent consensus vectors that exist entirely as high-dimensional math, refined in times in a black box before anyone moves, what happens when they're deployed in high-stakes environments.
That's a slightly terrifying thought.
Right. We might soon have fleets of autonomous systems operating in perfect, flawless harmony. But they'll be coordinating based on an internal language of agreement that human overseers fundamentally cannot read or interpret.
Wow. We'll be watching the flawless execution, but the actual negotiation, the consensus itself, will be completely invisible to us.
That is a lot to chew on. Well, thank you all for joining us on this deep dive. Keep questioning the evolving foundations of the AI tools around you because the way they think is changing faster than we can see.